Do we start on time or do we start on time? Well, that would mean
We have a few seconds, right, at best. And maybe
how exactly
9, yeah.
get on that.
Yeah, somewhat. All right. Good morning, RWC 2022. It's a pretty good start. It's actually really, really awesome to see so many people here. So yeah, we're Johan, Leila, and me. We've been organizing this event as general chairs. So let's take one slide. Give us one slide to tell you what it's like to organize RWC actually 3 times. So it kind of started in 2018 when I was at RWC. I talked to Emilia, who was one of the general chairs then, together with Anya, and she told me, this is actually a lot of work, but if I had to do it again, it would be super easy, because now I know how everything works. It's super chill, right? And at the time, I was organizing chess together with Iliana, who's sitting here in the front, and so RWC went well, chess went well, and sort of these words were resonating with me. I thought, if you actually know how to run an ISCR event in the Beurs van Berlage here in Amsterdam, Emilia said that's not a lot of work, right? So organizing Real World Crypto 2021, very quick thing, right? 20-minute operation, in and out, done. Didn't quite happen, so we did organize 2021. Most of you were at the virtual event. It's different. Then we organized it for January 2022, and pretty last minute had to postpone. And it's really awesome to see it now that it actually came together. Yeah, it was not quite that easy. And over the last few nights, maybe we didn't get as much sleep as we would have wanted to. Actually, the hardest thing until the end was to estimate how many people would come. Usually you have decent estimates from previous years, but first hybrid RWC, how many people show up in person? How many go remote? How many people are concerned that the Netherlands have no Corona rules anymore? How many are super happy that the Netherlands do not have any Corona rules anymore? We had no idea, and we made some sort of guess. And this is the only solid statistic that I have on the slides. We have 485 in-person registrations at the time when I made those slides, which was 5:48 a.m. this morning. And on the next few slides, there's a few statistics that are completely flawed because they are based on data from yesterday. And there were lots of registrations, in particular virtual, like remote attendance, but also in-person attendance, still coming in over the night. So as you can see, most of the registrations are in person. I believe that may change over the next couple of minutes. I don't know. So as I said, data from yesterday. There's really people from all over the world, as you can see here. Now, this is also a completely flawed statistic because you would think that you see all of these people from all over the world here in the room. And of course not. I mean, this is across virtual and in-person registrations. Very hard to do these statistics properly. You also see that most people are from Europe. And as far as I understand, I didn't do those graphics. This is way beyond my Excel skills. Most people are from Europe, and I think that counts also in the remote participants. You can see here that we have actually a lot of regular registrations, and you can see how this splits into regular and it says remote student twice. This is very flawed statistics that I get here. Okay, so there's some sort of split between regular and remote and students and whatever. Now, let's move away from those statistics. Let me tell you a few things regarding the organization of the event. So most of you will have checked the website of RWC, and you probably saw on the starting page and also somewhere in the travel information some recommendations on how to deal with COVID. Now, as I said, there's really no restrictions in the Netherlands anymore, but it would be nice if you read through those and follow those recommendations. In particular, wear a mask when you're not in the catering area. So I think in the catering area, we will be eating, we will be drinking. There's no point. But when you're not in the catering area, please wear a mask. When you're on stage, it's also, by the way, okay to not wear a mask. As you can see. When I'm talking about catering, so all the catering will be, most of you came from there now, will be across there in the Grote Zaal, so that means all the coffee breaks, the lunches. We will have a reception tonight, and my understanding is that afterwards you don't need a dinner reservation anymore. Tomorrow evening there's going to be a concert, and there will be drinks with the concert, there may be some light snacks, but you might want a dinner reservation after the concert. Now, if you're wondering where things are, so the blue marked room is where we are right now, and then sort of to the right on the ground floor, you see the Grote Zaal where the catering is. We also have several breakout rooms on the first floor. So if you want to retreat with a group of people to discuss stuff, maybe you have a project meeting running in parallel or whatever, there's 6 rooms on the first floor. That's rooms 1.1 to 1.6. And that's the rooms, well, I can show this now here. The remote people won't see this, but they don't care. Okay, so if you're staying around in Amsterdam, not just for RWC, but you do a little bit of tourism, we put some basic information, at least on tourism and on public transportation, on the website, so you might want to check that out as a sort of starting point for your venturing into Amsterdam. Also, if you're staying longer, next week there is the Dev Connect event by the Ethereum crowd, and it's sold out. But we can get 25 tickets for RWC participants for free. So if you're interested in this, I'm not posting the link to get the tickets because then, you know, stuff would happen. Just come to the registration desk. If you want to attend, we can get you set up with a free ticket for Dev Connect. Generally, if you have any other questions, come to the registration desk. There's always going to be someone there. We have a signal group to discuss stuff. If the people there don't know, we will figure it out. Now, last but not least, this event would not be possible without the generous help of various sponsors. So let me just briefly show their logos. I'm not going to go through all of them, but there's lots and lots of sponsors. And it's really amazing how, well, Nigel really manages to connect to all of these. Now Kenny. So Nigel did it for this event. Now it's Kenny. So now if you want to sponsor RWC next year, don't talk to Nigel anymore. Talk to Kenny. Nigel's out. All right, so it continues with the sponsors. And, well, that's basically it. So with this, I want to tell you, just enjoy RWC 2022 and enjoy Amsterdam. And now it's my pleasure to hand over to the first session chair, which happens to be Leila, who's standing behind me here. Thank you very much.
Good morning, everyone. It's my pleasure to have as the first session, Daniel Genkin said, it never starts with side channels, how come? Well, maybe something to thank to our program chair for, Elena. So yeah, we are kicking off with the session on SideChannel Attacks. And our first talk is Spectre Declassified, co-authored by a number of people, as you can see on this slide, but the most important one I will mention is the one that gives a talk at the moment, that's Sioli O'Connell. Welcome.
Uh-oh. Is it this one? Okay, cool. Okay. So my name is Sioli O'Connell, and this work was done in conjunction with authors from Georgia Tech, MPI, MDIA, the University of Radboud, and the University of Adelaide. So this talk is about how speculative execution interacts with declassification. And in particular, we show a surprising case in which, sorry, I forgot to do this. We show a surprising case in which we are able to speculatively leak data without having an out-of-bounds access. So let's see how this goes. So we begin with Alice sending a message to Bob, and Charlie can intercept the message. So what Alice does is she uses this mock cipher to encrypt her message to Bob. Now the way this cipher works is it applies a one-time pad, 1 bit at a time. Now unfortunately for Alice, it branches on key material. Now what's the problem with this? Well, the value of Alice's key influences the execution time of her program. And if Charlie can measure the execution time of the program, then he can infer some information about Alice's key. So that's called a timing side channel. And the go-to defense is called constant time programming. And the way this works is we try to ensure that there's no correlation between the execution time of the program and any secret data. So what we do is if we have secret data, we make sure that it cannot be used as the condition for a loop or for a branch. It cannot be used as part of an address for a memory access. And we can't use it as a parameter for some sort of variable time instruction. So for example, square root. So we apply constant time programming to Alice's program, and now it's safe. The problem is that this is ad hoc and requires the developer to be very careful about where they use secret values. We can mitigate this by using a security type system. What this does is it allows the developer to annotate the parts of the program that should be secret and the parts that they don't really care about, that can be public. And what it does, if we show Alice's original program, is it's able to automatically detect when you use a secret value, so in this case the key, and you use it in a way that it would leak the value to an outside observer. Additionally, it can recommend how to change the program. So here we see that it should remove the if, and now our program is nice and safe. So let's have a look at how values flow through our program. On the left, we have publicly typed values, and they are able to flow to the outside world. We don't care because by definition, they are public. On the right, we have secretly typed values, and we need to make sure that they don't flow to the outside world. And indeed, our constant time programming and our security type system ensures that this is not the case. So now we have a problem. At some point, we may want to take a secret value and actually send it to the outside world. In this example, we perform encryption, and we have some ciphertext, which is, we have some internal state, which is considered to be secret, and we would like to now expose it as the ciphertext. The problem is, when we set the secret variable state, and we try to assign that to a public variable, the compiler complains. It says, well, hang on a second. I don't know that this is safe. You're trying to leak or you're trying to set a secret value to a public variable, and that leaks it. How do I know that that's a safe operation? The compiler cannot automatically determine that. So what we do is we use a declassify statement. This acts like a typecast for security type systems. It takes a value that is secret and turns it into a value that is public. And the developer asserts that this is safe to do. Now, like a type coercion or typecast, this has no runtime effect. It's just a message from the developer to the compiler that this is safe to do. So now when we add declassification back to our diagram, we see that there is a path for secret values to reach the outside world, but they must pass through the declassify statement. And as we talked before, the only time that happens is when the developer asserts that these secret values are safe to turn into public, these secret variables are safe to turn into public variables and then can be leaked to the outside world. So now everything is safe. Unfortunately, in 2018, Spectre was published. And the key idea behind Spectre is that under speculative execution, the invariants of our program, or the conditions that it checks for, do not necessarily hold. So for example, here is the classic Spectre Gadget for Spectre variant 1. All it is it's a function that indexes into an array and it's bounds checked. So it won't index into the array unless it's inside of the length of the array. Once it does the index, we call this leak function. And this leak function just abstracts over the side channel leakage that we want to use. It could have been one of the three that we discussed earlier, or something else. It doesn't particularly matter for our case. It's just that we leaked the value somehow. Now, the key idea behind Spectre is that this body can be executed even if the condition is false. Now, what this means is that this index could actually be larger than the length of the array. And when that happens, this array index is now out of bounds. And we're not just loading some public value, we could load any value, any arbitrary value of our program. In particular, we could access some secret value and load it. Now what's worse is the value that we're loading, we have asserted to the type system that this is public and we're allowed to leak it. So what can happen is we load a secret value speculatively and then we leak it out through some side channel. Now of course the processor will at some time detect that this condition is actually false and kill this speculative execution, but we've already leaked the value and it's too late. So if we look back at our diagram, we now have a second way in which values can leak, secret values can leak to the outside world. So this happens when Spectre is used to smuggle a secretly typed value and then leak it into the public domain. Now fortunately, there are mitigations for Spectre, and for Spectre variant 1, there's a mitigation called speculative load hardening. Now the way this works, the way this works is that we instrument the program with the compiler to detect misspeculation. And if any misspeculation is detected, we then poison all additional loads. So let's look at how this looks with a Spectre Gadget. We apply all of the masking from SLH, and there's two main things that we care about. The first is this second green line here, and what that does is it maintains the mask variable. For each condition in our program, we recompute the condition using a special instruction that cannot be speculatively executed. So for Intel machines, this looks like a C move. For other architectures, it may be different. The second thing that's very important is that any access to memory, we apply this masking operation. And the way this works is we just do a bitwise OR with the mask. Now, in the case that the index is within the length of the array, that is that the body has been speculatively executed correctly, then the mask is simply 0 and the masking operation does nothing. However, in the case that the body is executed and the condition is actually false, mask gets set to -1, and now anytime we perform a memory access, we poison that value and set it to -1 as well. Now how does this look in our diagram? What happens is, anytime we try to use a Spectre attack to smuggle a secret type out to the public domain, SLH poisons that value. In effect, it cuts off the flow of secret types to the outside world. So, a lot of work has currently looked at how speculative execution interacts with secret values, but there's still a pathway for secret types to reach the outside world through this declassification. And to the best of our knowledge, no work has looked at how declassification interacts with speculative execution, and we aim to fill that gap. So back to our mock cipher. Let's consider what happens if this particular loop is predicted not to be taken. That is that we predict it will be taken, that is that the processor predicts that we skip this loop entirely. What happens here is that we skip the encryption itself, and now our declassification, rather than declassifying the ciphertext, declassifies the unencrypted message. And because we've now asserted that it's safe and public, we can leak this to Charlie. So if we look back at our diagram, we see that there is now a pathway through through speculative declassification. And because speculative declassification happens at a time the developer did not intend, it violates the security intent of the developer. And in particular, we could declassify a value that may still be secret. So let's look at a real-world example. So this is an implementation of AES, and AES has security parameters that allow you to modify the number of rounds that are performed. And we use a branch here to support multiple security parameters at once. So just like the previous example, we can predict that this branch is not taken and skip applying additional rounds of encryption. So now this declassification can declassify an incorrectly encrypted ciphertext. And what we show, and this can also be leaked to Charlie, and what we show is that if you get the incorrectly encrypted ciphertext and the correctly encrypted ciphertext, it is possible to recover the key. So how do we fix this? What we do is we insert a speculation fence into the declassification. So what is a speculation fence? It's a special instruction that ensures that earlier instructions need to execute correctly before later instructions execute. Or in other words, if we try to leak the ciphertext, those instructions cannot execute until everything before it successfully executes. So if we look back at our diagram, we still have a flow of secret values to the outside world, but it must pass through our fence declassify. And because of the way, because of the semantics of a speculative fence, this can only happen when the developer intended it to, and therefore it's safe. So we implement fence declassify and compare it to SLH. So SLH here is in light blue, and fence declassify is in dark blue. SLH plus fence declassify is in dark blue. And we implement this for a series of encryption algorithms. And what we see is that the performance impact is negligible. As an additional contribution, we look at optimizing SLH itself. And what we do is we take advantage of the security type system to try to minimize the number of masking operations. And we'll look at how that works right now. So here we have our Spectre Gadget, just as before, and we apply our masking. Now let's consider what happens if the value that we are loading into is secret. This particular leak cannot exist. And the reason why is because our security type system guarantees that anything we mark as secret cannot lead to a leak. It can go through a declassifier, but it can never go to a leak. What this means is that if we speculatively perform this array index and it happens to be out of bounds, we don't particularly care. It doesn't matter if this is the right value or the wrong value, it still can never leak. And because of this, we don't need to actually perform the mask. So when we apply selective SLH to two encryption algorithms, we see that as many as 95% of masking operations can be removed. So to summarize this talk, speculative declassification violates the security intention of developers. We show that it's a problem with a real-world implementation of AES, and then we mitigate the problem with fence declassification, and we show that the mitigation has negligible impact to performance. And then finally, we show that we can optimize SLH by taking advantage of the security type system to reduce the number of masking operations that are required. So thank you for listening to my presentation, and I'm happy to take questions.
Thanks for the talk. Does this work? Yes. I just would like to explain how this works. So please, if you have a question, if you could come to the mic there. Is that okay? Yes, please. Sorry, I should have said before, and people could have been there already. But, sorry.
Watson Sealants, what happens when value speculation is introduced?
Sorry, what was that?
When value speculation is introduced?
It's not something that we've looked at in this work. It'd be very interesting for future work.
Hello, thank you for your talk.
Thank you.
I was wondering, the declassify does a lot of heavy lifting here. And in particular, in the case where the security of a declassify would depend on some higher level property, like a nonce never being used twice, one declassify could be secure, while another declassify could not be secure. And I don't think this binary type system can capture this notion, right?
So tentatively, I would say I agree, but that's not my area. Where's Sanjay? Oh, he's right at the back there. He's the person to talk to. He does a lot of the formalization of the security type system. He'd be the one to talk to about this.
Okay, because I was wondering what happens if speculatively I manage to execute something like Cha-Cha, but using the same nonce, and then even if your type system proves this operation secure, it actually isn't.
I think in that case, what you would find is that the fence declassifier would make sure that you can't misspeculate an encryption of Cha-Cha 20 with the same nonce. So you would have to do this architecturally, and I believe that's that you start getting into the area where our security type system just makes no statement whatsoever.
Okay, I see. Thank you.
No worries.
Thank you. Do we have another question? Yes.
So you showed us a case where an out-of-bounds array read would incorrectly leak a secret value into a public variable. So is publicness or secretness, is it a property of a variable binding, or is it a property of like a region of memory? And
sorry to cut you off.
I was just, with that in mind then, is data considered secret by default?
So it's a property of the variable binding itself. And in the language that we use, which is fact, you're required to mark it secret or public. You can't, there is no default as far as I'm aware.
Okay, and last sort of question. Does this relate at all to the problem of pointer provenance that compiler folks are looking into?
I'm not sure, sorry.
Thank you.
Hello, my name is Armando. So the question that I have is that fence code is a well-known technique, but how did you ensure that the fence actually executes the instructions that the program actually is issuing?
Sorry, can you repeat the question?
When you use the fence code, so how do you make sure that the instructions that were previously issued by the programmer are actually executed?
So you're saying, I don't know if I have slides. Okay. So you're saying that how do we make sure that instructions before the fence are actually correctly executed?
Right.
So what we do is we use some sort of speculative fence. So for Intel, it's an L-fence instruction. And the semantics of that instruction are that the instructions before it need to be completely executed before instructions after it can be executed.
Yeah, but if someone tampers the program, so you are not sure that the instructions that were on the original program are actually executed.
So you're saying under the effect of somebody tampering the program.
Right.
I think that's a conversation to take offline.
Okay, thank you.
Awesome.
So I feel like there's been a lot of work on taint tracking and like just propagating this sort of state. Do you feel like this is kind of like a cat and mouse chase where like it's like there's a new speculative execution tag that comes out, you do something, there's like, would you say that this would be like a problem that's better suited to like the hardware level where like you have like, secret data and like non-secret data, and then like you kind of, go from there instead of just like, because you'll build something and then like there might be like a new Intel change or whatever and like it's kind of gone.
Mm-hmm. Oh boy. I think the best way to answer that is that that sort of like cooperation with the hardware vendors is like the topic of entire presentations and possibly entire conferences. It's a lot of there's a lot of stuff in there to unpack. I'm sorry that it's kind of like a unfulfilling answer.
Okay, thank you. I see a question in Zulip, but maybe you can take it offline afterwards.
Okay.
I think we should move on to the second talk. Thanks to the speaker again.
Cool, thank you.
Okay, our next speaker is Jan Jančar from Brno. That's another talk co-authored by a number of people. And we will find out what cryptographic library developers think about timing attacks, and it appears they are not that hard to mitigate. Jan, the floor is yours.
Thank you, Leila. All right, so my name is Jan. Hi, everyone. And I'm presenting work done in cooperation with all of these great people. Some are from Max Planck Institute for Security and Privacy, some are from IRISA, and some are from George Washington University. And I'm from the Center for Research on Cryptography and Security from Masaryk University in Czech Republic. And this is work on what cryptographic library developers think about timing attacks. But before I begin, if you want to check out the full paper, there's a QR code there, but also a link. So, timing attacks. Does this work? No, this doesn't work. Does this work? This works. So timing attacks, they have been around for a while. They're now more than 25 years old, introduced in this 1996 paper. And the way they work is they abuse timing leaks. So as was really nicely explained by the previous talk, they abuse that the duration of an operation depends on some secret somewhere, and that the duration leaks some secret information. Now, why this happens is mostly due to branches or memory accesses on secret derived values. There can also be variable time instructions, but those are sort of a smaller problem usually. And the way the attacker would get sort of to these leaks is through like measuring the whole operation, so something like either modular exponentiation in RSA or like scalar multiplication in ECC, or do like a cache tag on some iteration of this, and so on. But for this talk, we don't consider speculative execution at all, as it's a whole another beast, and this is just like pure timing attacks without speculation. Now, what's interesting for me about timing attacks is that they are still around. So even after these 25 years, just 2 years ago, there were these two groups of vulnerabilities, Minerva and TPM fell in. One was in smart cards and sort of cryptographic libraries, other was in TPM and other secure hardware, and those were really pretty serious timing attack vulnerabilities. There actually are techniques of avoiding timing attacks, again, as was really nicely explained by the previous talk. There's this constant time code practice where you avoid these things that will leak your secrets, so you avoid these branches and the memory accesses, and then you hope that the compiler doesn't optimize those away, but you don't really just have to hope. You can also test, so there are these tools for verifying a resistance to timing attacks. For this work, we have collected most of them like we collected all that we could find. This was not an easy task. There is no Wikipedia list of tools that can do this sort of stuff. So there is now more than 25 of them. They are some are like 10 years old, some are just from last year, and they have very different targets. So whether it's like they work on source code level or like a binary level, and they use very different techniques. So there's like dynamic instrumentation tools that instrument your code and then run it to observe its behavior, to test whether it's constant time or not. And there are also like formal analysis tools that use formal methods and things like symbolic execution to argue whether your code is constant time. And due to these reasons, these different techniques, the tools have very different requirements on your code. So some need stuff like code annotations, like secret types and so on. And they give very different guarantees. So some give only like statistical guarantees, meaning your code is likely to be constant time, but some give more stronger guarantees that really your code is really constant time. So all in all, like it seems that we know how to avoid timing attacks, right? We have tools to test resistance against timing attacks. So why are timing attacks still around? Is it that timing attacks are just not part of threat models of cryptographic libraries? Is it that the libraries don't know how to protect against them? Is it that the developers are unaware of these tools that could help them? Or why are the tools not being used effectively, right, generally? So, well, what we decided to do is let's just ask the developers, right? They are the ones that should know answers to these questions. They're the ones that would know the threat models of their libraries. They're the ones that would know how their libraries try to protect against timing attacks. And also, they are the ones that would use these tools. They are the ones that would fix timing leaks. So that's what we did. We decided to run a survey on open source cryptographic library developers. We focused on the most active contributors by number of commits, and in the end we invited more than 200 developers from 36 libraries, and we got 44 valid responses from 27 libraries. So here I would just like to thank all the participants of our research. Some of you might even be here in this room, in which case really thank you, or remotely. Yeah, without you this research wouldn't be possible, and also these libraries wouldn't be as good as they are. And if you're a cryptographic library developer and we didn't invite you, I'm sorry, we had to stop inviting at some point. So we have all these popular libraries that responded to our survey, and we also think that we really got the key developers we wanted to ask. So we got a lot of core developers, maintainers, or committers. So these are the people that would influence how these libraries sort of handle timing attacks and where they go. So in our survey, we first focus on the participant background, so their general experience in developing cryptographic code and stuff like that. But then we focused on the library. So the developers' role in the library, as well as how the library makes design decisions. So whether there's committee or there's some voting and how these are made. Then we focused on the library's threat model with regards to side-channel attacks, and then asked developers about what timing attack protections they have in their library and how these work. And finally, we also asked them about how they test these timing attack protections and whether they actually do that. Next, we asked them about their awareness of these tools, so these 25 tools that I presented on a slide just a few back, and whether they're aware of these tools and how they learned about them. If they knew about these tools, we also asked them if they tried to use them and what are their experiences with those tools. Now, as we suspected, quite a lot of them wouldn't have used any of the tools. We also wanted to get their opinion on the tools somehow, so we presented them with properties of these three groups of tools. So these are three very distinct groups of tools based on how they operate. These dynamic instrumentation-based tools, statistical runtime tests, and formal analysis-based tools. And they have very different properties on the requirements on your code that they need to run, but also the guarantees on the results they give you. And then we asked the participants about their likeliness of use of these groups of tools and their reasoning. Finally, we asked them about their general thoughts on timing attacks and an opinion on our survey. And I must say that most liked this sort of research and liked our survey, so that felt really nice. So what did we find out? Luckily, we find out that developers know about timing attacks. So 100% of our sample knew about timing attacks, although their opinions varied. So from this statement that got into the title of our paper is that timing attacks are not hard to mitigate, at least using some specific compilers. I would really like to know what compilers those are, because I don't know any that make this specifically easy, but so if this is you, please let me know. But also, so the opinions varied from this sort of spectrum. On one side, there was this strong opinion that it was totally obvious for everybody right from the start that protection against timing attacks is something that's necessary for cryptographic libraries. So that's a strong opinion on the necessary protections against timing attacks. But also to this more skeptical that for many cases, there aren't enough real-world attacks to justify spending time on avoiding timing leaks. And so the last code has the world's real world in it, and I actually wonder what the opinion of this real world crypto audience is on timing attacks. I might run a poll during the lightning session or something like that. But now, even though the opinions varied of the individual developers, the libraries mostly considered timing attacks in their threat model, so they included them. 23 libraries did that. Although they often differentiated between remotely exploitable and locally exploitable attacks. Although the line there is fuzzy, some libraries outright excluded local attacks out of their threat model, but most libraries were just sort of giving higher priority to remotely exploitable attacks than to locally exploitable attacks. Now, the reasoning for including timing attacks in their threat model varied. There was this general feeling that timing attacks are a relevant threat for cryptographic libraries. There was this more specific statement that the fear of loss of reputation, as this quote puts it, it's never fun to be the bug that a new research paper is talking about exploiting. And I would feel like, yeah, it's never fun to be that. But also, some libraries explain that the target environment of the library is such that it's just exposed to timing attacks and it needs to be protected. So caring about timing attacks is one thing, but actually claiming resistance against them is another. And here we see that the 13 libraries claimed full resistance against timing attacks, which is a pretty strong statement. I'm surprised that so many were so strongly opinionated on this. And about 10 libraries claimed partial resistance against timing attacks. And this partial resistance can be sort of a problem from the point of view of the user of the library. If you want to use this library, how do you know you are using the constant time part of it and not the leaky non-constant time part of it, right? If it's not documented somewhere, it's really hard to not shoot yourself in the foot while using such a library. And some libraries just outright said that they are not constant time. Now the reasoning, they use various different protection techniques to avoid timing leaks, but mostly there was this constant time code practice. So as I explained, avoiding conditional branches and lookups on secrets, and then hoping the compiler doesn't mess this up. But also there was this mention of using a constant time algorithm. So for something like a scalar multiplication on ECC, there are various known regular constant time algorithms that you can just outright use. I would just mention one more countermeasure that one particular library mentioned, and that is random delays. So this library was really only just using random delays, and I don't think that's a really good countermeasure. So I invite all of you to try to figure out which library that is, and maybe there are some timing leaks there, maybe there are interesting timing attacks. I don't know. I didn't really have time to look at that. But that's enough for the libraries. Let's look at the tools. So most developers heard of at least one tool, and these were the three most popular tools with ctgrind, ctverif, and memsaf. So ctgrind is based on Volgrind, based on this memcheck tool in Volgrind that you can use sort of to verify resistance against timing attacks. But from all the other tools, the rest, the 22 tools that remain, those tools were unknown. So only one or zero developers knew about those tools. So it's really hard for a tool to be used if no one knows about it. On the other hand, the approach of ctgrind is so simple that some developers claim that they independently came up with this approach without even knowing that the tool existed. So if you want to know more about this approach, just hit me up. I can explain it later on. But only, even though the developers sort of knew about some of these tools, only 19 tried to use them, most explaining that they cannot use them because they lack time, right? That was the most often given as the reason why they cannot use these tools. Also, some explain that some of the tools are unable to ignore known issues. So like you're trying to analyze code, you know there is a non-constant time part there, you want to just ignore that and focus on some other part. Some tools cannot do that, and it's really a problem. You are getting too many sort of false positives, and you cannot get clarity out of that. But also it's hard to use a tool that's not available, and it's hard to rely on a tool that's not maintained. So those were the other reasons why these tools weren't used. So the developers are also sort of outright unlikely to use some of these tools. So when asked about these three groups of tools, these formal analysis, statistical, and dynamic tools, the developers were unlikely to use formal analysis tools, and this was because they were perceived as way too much effort. So 22 developers claim that these are way too much effort, and this is really nicely summarized by the quote that formal analysis tools are not really usable by mere mortals yet. And I've tried to use some of these tools. I would mostly agree. You really have to know what you're doing, but yeah, I cannot expect that from people that are not focused on formal methods. For the dynamic and statistical tools, the developers feel that there is a more acceptable trade-off between the effort and the guarantees these tools provide, but they like the guarantees of the dynamic instrumentation tools, which are a bit stronger than the statistical ones, and so they would like to use those more. So we've identified this sort of leaky pipeline of developers trying to mitigate timing attacks using these tools, with 44 developers entering and only 17 developers meaningfully using these tools to prevent timing leaks in their respective libraries. So what can we do about this? What can we fix? What can change? Well, the tool developers should make their tools more usable. The tools need to be available in the first place. There needs to be documentation. They need to be easier to install. So to make this effort for developers easier. And also the tools need to be promoted at appropriate venues. So something like real world crypto is a good place, I feel like. So I hope I'm doing a good job here. And also crypto developers need to use these tools, ideally in an automated way, in CI or something like that. And they need to eliminate all timing leaks, even if these leaks sort of feel not likely to be exploited at the moment, they can turn to be easily exploitable very easily. And also marking secrets in code is really helpful because then you can use these tools which require this sort of marking very easily. Now, compiler writers also have something to do. I didn't talk about compilers much during this talk, but compilers can introduce these timing leaks in even seemingly like constant time code. So compilers should just sort of add the support for these secret types, as we mentioned in the last talk, and then do not introduce timing leaks based on these secret types. And also compilers should sort of give more control to developers to avoid these timing leaks. And finally, standardization bodies, so like NIST, in case of NIST post-quantum, crypto standardization effort should encourage submitters to use these tools. I mean, they're available, so why not? And also, we feel like they should require constant time code, that it should just be the baseline of the entry, of the code entry to the standardization effort, that it should be constant time. Because how can we then expect these libraries to be constant time if even the sort of the original design primitives are not? So we have studied what cryptographic library developers think about timing attacks by running this survey, and we sort of found out that they know and care about timing attacks, but do not know these tools that are needed for verification of constant timeness. They do not use these tools, mostly due to lack of time and perceived huge effort. We have identified this leaky pipeline that there is of these developers, and also that they really fear the effort needed for formal analysis tools. So that's it for me. Thanks for listening, and I'm sure you have some questions.
Okay, I'd like to invite people with questions to approach the mic. Yes.
Hi, thanks for the nice talk.
Thank you.
So you mentioned, and we saw the table at the beginning, that there are very many tools that are used for checking constant time, but not much is done on compilers to convert C code to the final binary without optimization that breaks it. Why do you think this is happening, and are you aware of any work that is done towards this direction?
So yeah, thanks for the question. There are tools that are sort of like compilers that do not introduce timing leaks, but they usually use their own language. So there is like the previous talk used FACT, which is like a custom language where you have these secret types, and then you compile it, and then it keeps the constant timeness, and it doesn't break stuff. So there are tools, but they use custom languages. And also developers here, there were some sentiments that using custom languages is something that they don't like because they have to integrate it with the rest of their C stuff. And so these tools don't see that much use as well. And why compilers don't really support this, I think there's a big divide between like compiler writers and like crypto side-channel people. I don't think there is much overlap there, and sadly this results in not supporting this stuff.
Maybe quickly one question from Zulip while you get ready. By Alexander Anzala Yamayako. Can you give an estimate on how many of the timing attack tools you identified were first, actively maintained, and second, industry ready for some value of industry?
Actively maintained, wow. A few. Yeah, I would say, let's say, I would like the list, but I don't have the slides. 5 would be, I would say, actively maintained, and industry ready. Wow, that's what is industry ready? Let's put it this way. Some of the tools are used in CI, so continuous integration of cryptographic libraries. So I know Amazon S2N uses CTverif. One of the co-authors of CTverif, I think, works at Amazon, so yeah, so they have that. But also some open source cryptographic libraries, they use CTGrind, they use MEMSAN in their CI, so that's as industry ready as you can get.
Yeah, you can get back to Alexander in Zulip later on. Yeah, please.
Hi, this is Peter. Thank you for your overview.
Thanks.
So I was wondering, how many of these tools have actually tried to integrate themselves with the existing, turn a bit around, instead of developers adapting these tools, the tools adapting to libraries?
Oh, so I've worked with these tools, and I've some of them, right? There's 25, so that's too much to work on at once. But I've integrated some of them to a few open source libraries. Like they're not upstreamed yet, but I have the code, and I'm working on that. So yeah.
Was that reasonably easy to do for
Sorry?
you? Was it reasonably easy for you to do as someone who made a tool? So would it be more time efficient or more efficient for for you to implement this into the libraries? Or?
So you mean like whether it's more efficient to go like the tool developers should implement this stuff into the libraries rather than the crypto developers should take the tools, right? Well, maybe, but so the issues I had with the libraries is that I was trying to implement like CT grind in NSS, and I don't know NSS, and I don't know their APIs and whatnot. So it took me like a huge amount of effort to understand the library. So I know the tool, but I don't understand the library, or I know the library, but I don't know the tool. So yeah, okay.
Thank you.
Thanks.
Thank you. We have maybe one more question from Zulip. Anders Nilsson asked, timing attacks, which tools would fit to check trusted execution environments, TEEs?
So it depends on like, thanks for the question, but it depends on whether you have like access to the code or you are trying to check a running enclave or something like that. But if you have access to the code, then all the tools that work on the code level would work. And if you can compile a binary for these tools, then also the binary level tools will work. So I would say most tools should work. I mean, there are clarifications. Some of the tools like don't support, I don't know, like floating point arithmetic or dynamic libraries, and they have these limitations and whatnot. But yeah, most.
Thank you. I think it's time to move to the next talk. Let's thank the speaker again. Thank you. The final talk in this first session is on, again, SideChannel attacks. Lend me your ear, passive remote physical side channels on PCs, so somewhat different side channels. And Daniel Genkin and Rui Schuster will give the talk.
Right. Thanks, Leila, for the introduction. My name is Daniel Genkin, and this is Rui Schuster. And our title is Lend Me Your Ear, Passive Physical Side Channel Attacks on PCs. And this would appear at Usenix Security 2022, and is joint work with Noam Nissan and Eran Tromer. So, at a high level, side channel attacks come in two main flavors. The first one is what we call software-based side channels, and this is an example of microarchitecture attacks that we've seen in this session, where the victim and the attackers have some contention on some CPU resource, in this case this blue gear, and the attacker times the contention induced by the victim and deduces information about what the victim is doing. And this comes not only in the microarchitecture world, but as the previous lecture mentioned, we can also talk about timing analysis or packet analysis, and pretty much any shared resource between attacker and victim can be exploited to induce contention and to deduce information about what the victim is doing. So those are software-based channels. In addition to it, there is a parallel world of side channel attacks, which are known as physical side channels, measuring the device's power consumption, electromagnetic emanations, acoustic emissions, things that this device does and emits involuntarily as it does computations, for example, consuming power or emitting EM. Now, between this dichotomy, if we start talking about physical side channels, well, it's literally an attacker with an antenna pointing it at a laptop and trying to extract what this laptop is doing. So they have very different properties than microarchitectural side channels. And first of all, don't need to execute code on the target, right? That's the greatest thing. You don't need to interact with the target in any way. Just put your antenna dish near the target and passively observe whatever the target is emitting. So that's a blessing. But in some sense, it's also a curse, because now you need physical proximity to the target, and you can't run them over the internet purely by software against a target that you don't even know where it is. And that's how we typically view physical side channels. And we can even argue that we can protect against physical side channels by removing proximity. And what we're going to do today is try challenging this assumption. And in particular, what we're going to show you is a remote physical side channel without any attack code running on the target. So we're going to measure the emissions of this laptop right here without running any code on it and any attack code on it, and without assuming we have physical proximity over it. So how can we do such a thing? Well, the first observation is, here's a laptop, and what I'm going to claim is that laptops can measure themselves. And how do you make a laptop physically measure itself? Well, as we all know from the COVID-19 pandemics, laptops are typically shipped with internal microphones. And we all know these microphones by now, because this is our only voice connection to the outside world. And if I were to look how this microphone is wired, so let me remove the keyboard, then I would find on the motherboard an audio interface. And the microphone is physically wired to that audio interface with traces. And what I will also see on that very same motherboard what I will also see on this very same motherboard is the processor. Okay? The thing that emits EM and is a heavyweight consumer of electricity. Now, if this picture right here looks very similar to this picture, which is a proper EM analysis with a proper EM probe, well, that's not by accident. That's exactly what is happening here. We have essentially building computers with EM probes in them hooked up to a measuring device, which is the audio interface. So now, every time I turn on the audio recording, well, guess what? I'm picking the sound of the voice, or of the speaker's voice, but also any electromagnetic emission emitted by the processor, which I can then measure. And making it even worse, well, as we all know, Zoom is part of our life. So audio picked up by my internal microphones is also often shipped across the internet to various places. For example, to the attacker. So now our voice over IP attacker can measure physical emissions from this laptop by simply monitoring the analog signal being shipped to it over the VoIP over IP channel. And that's exactly what we're going to show you today. So to show you that this actually all works, we've prepared a bunch of demos and made the demo gods with us. Okay. So we are going to measure the, thank you. So we're going to measure, okay. So we're going to measure the electromagnetic emissions from this laptop, from our attacker station, which is located conveniently behind it, and these two machines has a voice over IP connection between them. Now, what I'm doing here is that whatever the local microphone in this laptop picks up, we're piping it into the attacker station, and then instead of showing it, instead of playing it, which would create a really nasty echo in the room, what I'm doing instead is I'm visualizing it in a form of a spectrogram. So this diagram is called the spectrogram. The vertical axis is the time axis, and the horizontal axis is the frequency axis. So if I whistle, you see my whistle showed up, and people usually whistle at around 1 kilohertz, so that's that. And the more yellow something is, the stronger the signal is at that point in time and frequency. And by the way, you see that this diagram is live, so this microphone is actually picking up my voice. But in addition to picking up my voice, this microphone also picks up something else. So my voice stops at around here. This is why you see this area to be a bit yellow. But there is also things here. And this is relatively high frequency EM that is being picked up as this laptop just emits it. And if I were to run a small test program on this machine, then as soon as I hit enter, you see the screen changed, and we have a very cyclic pattern. And every time, what you're seeing here is that this is a program that does 1 second loops of memory instructions, followed by 1 second loops of multiplications with some halts in between. And we can see that we have here a bright region, which is memory instructions, a darker region, which is multiplications, and halts in between, which show up, which light up the entire frequency range. So we can clearly distinguish between operations. But we're not in the business of distinguishing between high-level operations. We're at the business of extracting keys and doing fun stuff with signals. So now I'm going to hand it over to Roy, who is going to show you how to actually use these effects in practice in mounting cool attacks.
Thank you, Daniel. Thank you. So the first thing that I'm going to do is I'm going to start running the next demo because it takes a few seconds to run. Okay. So we are going to show how to actually exploit this side channel. Sorry. Okay, and we are going to mount a website identification attack where our victim is accessing some website like Twitter, and at the same time they are on a Zoom call or a voice over IP call with our attacker, and audio is being transmitted from the victim to the attacker over the internet. Now the attacker, in our case, will be running a neural network to extract the identity of the website. Now, in the demo that I'm showing you, there won't be a neural network, obviously. What we will see is the spectrum of two websites that are now being visited by our victim device as I speak. And we are going to see that they will have very distinct differences between them. Okay, so this is our attacker device. This is going to take a second. All right. So you can see that these signals are indeed different. They are treated the same way, but they have, visual difference between them that we can see. Of course, what I'm not showing you, and you have to trust me, is that these differences are consistent. So if I had the victim visit Google multiple times and I had the victim visit YouTube multiple times, you would see that the signals of YouTube are more similar to each other than they are to the signals of Google. And so we can use this to actually distinguish between them. Now, sometimes in pairs of websites, we won't be able to see it with our eyes, but still the neural network will be able to detect these differences. And our primary result here is that using convolutional neural networks, we were able to attain a 94% accuracy for 14-way classification between websites. So we can distinguish between different activities or different websites on the victim device remotely. And we have a deeper characterization of these numbers in the paper. Now I'm going to talk about cryptographic key extraction. So here, it's a very similar setup. We have the victim device actually signing some messages, cryptographically signing some messages, and voice is being transmitted to the attacker, and the attacker is going to run some machinery in order to actually extract the key. Now, why is that even possible? We are going to attack an ECDSA implementation by libgcrypt. ECDSA has key generation, verification, and signing, where the signing has this scalar by point multiplication operation where the scalar is a random nonce that is supposed to be kept secret. So since it's supposed to be kept secret, we have a constant time implementation. However, as exposed by Minerva, there is a bug in this implementation that basically allows us to see a linear dependency between the duration of the signature and the number of leading zeros in the key. So in other words, for short signatures, they indicate that there are many leading zeros, and if we can detect short signatures, then we can detect nonces that we know a bunch of their bits. So how can we use, how do we detect short signatures? The first thing we do is we process the signal in the time domain, then we pass it through a few filters, and we get this right-hand time domain signal that has this valley in it, and the duration of the valley corresponds to the signature time. Unfortunately, it is very, very noisy. It's quite a noisy estimate. So what are we going to do to denoise it? We are going to attack deterministic ECDSA, or RFC 6979, where the nonce is derived deterministically from the key and the message. And our attacker we are going to attack a victim that signs the same message multiple times. We are going to group the attacker records traces of each signature. They are grouping the traces by the message. And then they are performing outlier rejection and averaging to denoise the duration estimate. And now we're going to select the shortest signatures, which again, short signatures are signatures for which we know the first several bits. This was sufficient to run the lattice attack of Albrecht and Henninger, and we could extract a key from traces of 20,000 signed messages. The last attack I'm going to talk about, if I have time, is an attack against our killer app. It's an attack against in the game. It's a cheat in the game, Counter-Strike. Counter-Strike is an esport, or it could be considered a textbook example of an esport, where it's played competitively. Some people take it very, very seriously. And it's a first-person shooter, so what our attacker will try to do here, and again, the attacker is a similar setup where the attacker has a voice over IP call with the victim, and it actually makes sense if the attacker is in the game playing against the victim. Then if they're one-on-one playing, then it makes sense that they would have a voice over IP call between them. The attacker is trying to find where the victim is in the game. It's like a game where you are a shooter and you're looking for the other person. The reason and of course they want to find them and destroy them. And so the reason for why this is made possible is because in this game, I'm going to be a little inaccurate and say that when the attacker is close to the victim, for some meaning of the word close, the victim's computer is actually rendering the attacker's avatar in the game. And whenever that happens, the attacker can pick up on that signal. So all the attacker has to do is move near some object. If they detect that the victim is now rendering their own avatar, then they know that the victim is behind this object. Counter-Strike is a game where there's a bunch of trucks and walls and objects you can hide behind, and so the attacker will try to detect where the victim is. And this is not going to be a live demo, but it's going to be a video of this attack, where you can see that whenever the attacker is in a truck, and whenever they are on the right-hand side of the truck, they see this zebra pattern. And when they're on the left side of the truck, the zebra pattern disappears. And the zebra pattern is happening because the victim is rendering the attacker's avatar. So the attacker basically knows that the victim is on the right-hand side of the truck, and they are going to basically move around the truck and kill them from behind. So, yeah. And with this, we conclude, and yeah, you should check out our paper, and we'll take questions now. Thank you.
Yes, questions for Daniel and Rui?
So how should we protect against this?
That's a good question. Do you want to take it?
I mean, so the other, what we demonstrated here is essentially, from a cryptographic perspective, that this is a timing attack. Okay, so first of all, constant time code and all the good stuff from the microarchitecture world needs to be ported here so that you don't start mounting timing attacks using the EM signal as a proxy. So that's one. But two, there is a slight shift here in terms of what is believed to be possible versus what we just did. This is the first example of a physical attack mounted across the internet without any attack code running on the victim. Now, this specific one, it's a toy. I'm not going to argue that this is something that you should be awarded by tomorrow. But it means that it is possible, at least in principle, to mount physical attacks across the internet. And now the question is, what else is in our machine? What else leaks? And what the attacker cannot observe? And that's, of course, future research.
Thank you.
Okay, thanks for the talk. I'm Giorgio. I just have a small question. Did you find that if we add a certain amount of noise to the data, it would become impossible for the neural network to detect the attacks, the changes, I mean?
Well, it's possible, but if we did experiment with running different programs in the background, and also, well, you saw that we were just talking, and our victim did pick up on the voice. So these types of ordinary noises don't affect the attack. It's possible that if you really try to introduce noise, and again, that would, like, I mean, without any hardware measures, what I can see is, like, you can, for example, like, make the CPU much more busy, then maybe you can confuse the neural network eventually. It is 94%, it's not like 100%. So I can imagine a scenario where more noisy signals will result in lower accuracy.
All right, thanks.
Maybe.
Hi, thank you for the talk. I'm curious, so many VoIP protocols have like high-pass filters or other sort of like space-saving or time-saving filters. Do you have a sense of which codecs specifically are most amenable to this attack?
I'm sorry, I couldn't hear you the last of the question.
Yeah, which codecs are most amenable to this kind of attack?
What was the name of that codec?
I don't remember the name of it.
Yeah, but it's the codec that well, okay, there is a slide on this actually, so let me pull it up.
I saw you had mumble on it, so I'm wondering if it's like speaks or
right. This is so a lot of our experiments were made with mumble, but we can see the leakage from all the common, you know, software that you would use for voice over IP calls.
Great. So it's an argument between how close your microphone is and how good your analog setup is. This wasn't designed for this, right? Versus how the codec is configured. Mumble's codec you can configure particularly friendly, which is good enough for a live demo in a room full of people, and it doesn't fail even though you speak over it. But as you see, most software has some sort of leakage, and now it's an argument about parameters. It's there. It's usually there. Now, is it good enough or not? That's a separate question.
Great, thank you.
Maybe try to have a short one, both of you.
Thank you. Very interesting. I was wondering, are some manufacturers more susceptible to this attack than others?
Sorry, I didn't get that.
Are some like laptop models more susceptible to this attack than others?
So again, there is a slide. You're slowly decompressing what we compressed because we're running out of time. It's common. It's rather common. And how is it in your laptop versus this? I don't know. It's a game of numbers again.
And are some manufacturers not affected at all? Did you investigate, and were there like manufacturers that were totally okay?
Sorry?
Let's say, like, is Apple affected by this, for example, or all the manufacturers?
So there are vendors with better pipelines where we could not see it by eye, and then we gave up instead of running something more complicated that would extract it, because there are vendors that you can just see it.
Okay, last question.
So I've seen papers before that try and geolocate videos by listening to the 50 hertz frequency to try and detect the electricity in the local area. Did you try and do something like that, try and geolocate laptops?
No, we haven't, and that's actually super interesting. The electric interference signal, the 60 hertz, is a forensic tool used by most police departments these days. And yeah, that would be a very interesting topic. Come talk to us after if you'd like.
Thanks. There is one
question. And we were stuck at the same location because of pandemic, so it was kind of hard to do.
There is one question in Zulip. Maybe you can answer it offline, because I think it's time to go for a coffee break. Let's thank to the speakers and all the speakers. See you here in half an hour.